Hello friends. In the last lecture we have discussed about the collisions, about the coefficient of restitution, the final velocities of two bodies which are in head-on collision, that is which the final velocities of bodies in one-dimensional collision. Now today in this lecture we are going to discuss about the collision in two dimension, that is when two bodies are colliding but they are not in the same straight line, they are not in one dimension. The initial velocities and final velocities are not in a same straight line, but the direction of velocities, initial velocities, the direction of the final velocities are different. So such collisions are two-dimensional collisions, or they are also called as non-head-on collision. Now, we are considering two bodies of mass m1 and m2. So this is a body of mass m1 and another body of mass m2. Mass m1 is moving with initial velocity u1 and mass m2 is moving with initial velocity u2. See the directions of the arrows. The arrows are having different directions. That is, the direction of the two bodies are not in a same straight line because hence the collision is two-dimensional collision. So this is u1, the velocity, the direction of velocity of m1, and u2, the direction of velocity of mass m2, and this is the line of impact. This is the x-axis is the line of impact, and with respect to the x-axis, the velocity, initial velocity u1 of mass m1 is making an angle alpha 1, and with respect to this line of impact, the initial velocity u2 of mass m2 is making an angle alpha 2. Now, after collision, the direction of the velocity of mass m1 is v1 and the direction of velocity of mass m2 is v2. v1, the velocity v1 is making an angle of beta 1 with the line of impact, and the velocity v2 is making an angle of beta 2 with the line of impact. So, these two bodies are colliding, but this time the direction of the collision is two-dimensional collision. To apply the law of conservation of linear momentum to this two-dimensional collision or a non-head-on collision, here for this initial velocity u1, we separate according to what we have studied in the chapter scalars and vectors or the mathematical methods. We know that any vector can be separated into two perpendicular components. So this u1 vector, now we are separating into two perpendicular components along the x-axis and along the y-axis. So that is along the line of impact and along the common tangent. So this u1 we separate into two parts, that is u1 sine of alpha 1 and u1 cos of alpha 1. These are the two vectors or the two parts in which we are separating this initial velocity u1. Now, similarly, this initial velocity u2 we would separate into two parts. So this initial velocity u2 we would separate into two parts, that is u2 sine of alpha 2 and u2 cos of alpha 2. Now similarly, this final velocity v1 we would again separate into two parts. v1, now this is the final velocity v1 is making an angle beta 1 with the line of impact, and final velocity v2 is making an angle beta 2 with the line of impact. So here when we separate this v1 into two components, it will be v1 sine of beta 1 along this direction and v1 cos of beta 1 along this direction. Now here for v2, again the vector is v2. So v2 we are separating into two parts, v2 sine of beta 2 along this direction and V2 cos of beta 2 along this direction. So in this way, we have now separated the initial velocities u1 and u2 and the final velocities v1 and v2 along which are in two dimension. So we have separated their dimensions. In very much familiar words, we can say along the x-axis and along the y-axis, we have separated the initial and the final velocities of the two colliding bodies having masses m1 and m2. So now we would apply the law of conservation of linear momentum along the x-axis and along the y-axis, that is along the line of impact and along the. So according to the law of conservation of linear momentum, we will write the initial momentum along the line of impact. So we have m1 is the mass of the first body, m2 is the mass of the second body. So along the line of impact, we would be writing m1 u1 cos of alpha 1 plus, now this body is colliding with this body. So m2 u2 cos of alpha 2 is this is actually we are considering along the x-axis. So m1 u1 cos of alpha 1 plus m2 u2 cos of alpha 2, this is equal to, now we are discussing about their final velocities along the line of impact or along the x-axis. So this is m1 v1 cos of beta 1 plus m2 v2 cos of beta 2. So this is the equation. Now we will take our discussion to the y-axis, that is along the y-axis, that is along the common tangent. Now here u1 sine of alpha 1 is balancing v1 sine of beta 1 and u2 sine of alpha 2 is balancing v2 sine of beta 2. So we write the momentum there according to the momentum. We would write for the law of conservation of linear momentum along the y-axis, we would write m1 u1 sine of alpha 1 is equal to m1 v1 sine of beta 1, because these two vectors are balancing each other. Also, these two vectors, that is u2 sine of alpha 2 and v2 sine of beta 2, are balancing each other. Hence, we would write according to the law of conservation of linear momentum here m2 u2 sine of alpha 2 is equal to m2 v2 sine of beta 2. So in this way, we have separated the two dimensions. So now the formula for the coefficient of restitution, which we have derived initially, is E is equal to minus of V2 minus V1 upon U2 minus U1. So for this collision in two dimension, we would be writing the coefficient of restitution here as E equal to minus of, for V2, we would be writing V2 cos of beta 2 minus V1 cos of beta 1 upon U2. For U2, we would be writing U2 cos of alpha 2 minus U1 cos of alpha 1. So in this way, we would be writing the coefficient of restitution. So this is the coefficient of restitution along the line of impact for two bodies of masses m1 and m2 which are colliding in two dimension or which are in non-head-on collision.
A shell of mass 3 kg is dropped from some height. After falling freely for 2 seconds, it explodes into two fragments of masses 2 kg and 1 kg. Kinetic energy provided by the explosion is 300 joules. Using g equal to 10 meters per second square acceleration due to gravity, calculate the velocities of the fragments. Justify your answer if you have more than one options.
So we are discussing the problem 3.7, and given in the problem is there is a shell which is of mass 3 kg and it falls for 2 seconds, and after 2 seconds it explodes into two fragments of 2 kg and 1 kg. Now the kinetic energy due to the explosion or provided by the explosion is 300 joules, and they have asked us to find the final velocities of the two fragments of 2 kg and 1 kg. Now, initially the velocity of the shell was 0, and then it was dropped from some height, and after 2 seconds it has broken into two fragments. It has exploded into two fragments. Hence, we can use the formula, that is according to the first kinematical equation, we have V is equal to U plus AT. Now, and we have to consider here G is equal to 10 meters per second square, because the earth is pulling the shell by the acceleration due to gravity 10 meters per second square. Hence, now what will be the velocity of this nut, of this shell, when after 2 seconds? So, V is equal to U. U is what? U is the initial velocity. Here, the initial velocity of this is 0. So, this is 0 plus A. A is the acceleration. So, that is equal to 10 into T, time is 2 seconds. So, V velocity is 20 meters per second. So, at this point, when the shell arrives and now when it is breaking, it is exploding into two fragments, its initial velocity of the two fragments. So, the initial velocity of the two fragments when they are just breaking. So, the initial velocity U1 and U2 of the two fragments, which is U1 is equal to U2 is equal to this V is equal to 20 meters per second. So, the initial velocity of both the fragments of 2 kg and 1 kg is 20 meters per second. Now, we have been asked to find the final velocities. So, now according to the conservation of linear momentum, because we know that the linear momentum is always conserved. So, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Now, m1 is of mass 2 kg, u1 the initial velocity of this 2 kg is 20 meters per second. So, this is into 20 plus m2 is the mass of 1 kg. So, this is 1, u2 the initial velocity is again 20. This is equal to m1. m1 is 2 kg into v1. So, the final velocities we have to find. We don't know. So, v1, 20 v1 plus 1, the mass m2 is 1 kg. So, m v2. So, here we have 40 plus 20 is equal to 20 V1 plus V2. So, 60 is equal to 20 V1 plus V2. This V2 we can write as 60 minus 20V1. So this is one equation which we have found out between V1 and V2. Now, according to the problem, the kinetic energy provided due to the explosion is 300 joules. Therefore, the final kinetic energy minus initial kinetic energy is equal to the kinetic energy provided due to the explosion. So, final kinetic energy is half of m1 v1 square plus half m2 v2 square minus half m1. Now, because the u1 is equal to u2, u1 is equal to u2. So, let this be u. So, half of m1 u square plus half of m2 u square. This is the initial kinetic energy. The initial velocity of the fragments is the same, which is 20 meters per second. So, this is equal to the kinetic energy provided, which is 300 joules. So, this is the 300 joules. Now, half of for m1, we would be writing 2 kg. So, this is 2 into v1 square plus half. m2 is 1. So, 1 into v2 square. This is minus half m1 plus half m2 for u square. So, half m2 into u square is 20 square. This is equal to 300. Now, taking half common. So, half of 2v1 square plus v2 square minus half m1 plus m2 into 20 square. This is equal to 300. Now, taking half outside. So, 2v1 square plus v2 square minus, now m1 plus m2 is 3 kg. So, we write here 3 into 200 square is 400, 20 square is 400. So, we write here 400, we complete the bracket, this is equal to 300. Now, multiplying the equation, both sides of the equation by 2, we get here 2v1 square plus v2 square minus, this is 1200. This is equal to 600. Now, we get 2v1 square plus v2 square. This is equal to, this 1200 we shift here. So, we get 1800. So, these two equations we have got for finding the v1 and v2. So, this is equation 1 and this is equation 2. So, we have to solve them now. Now, here we put the value of v2 from 1 in the equation 2. So, we get 2v1 square plus 60 minus 2v1 square. So, this is for v2 we have written. This is 1800. So, 2v1 square. Now, we expand this according to a minus b square. So, a square minus twice ab plus b square. So, we get 600 square minus 2 into 60 into 2v1 plus 4v1 square. So, this is equal to 1800. Now, taking v1 square on one side, we get 2v1 square plus 4v1 square plus 60 square, that is 3600 minus 6 into 2, 120 into 2, that is 60 into 2, 120 into 2 is 240 V1, this is equal to 1800. So here we add up 6V1 square minus 240, 6V1 square minus 240 V1. We take this 1800 on the left side, so we get 3600 minus 1800, that is 1800. This is equal to 0. Now dividing the whole equation by 6. So dividing the whole equation by 6. So this we get cancel. Here we get 3. This is 4. So we get V1 square minus 40 V1 plus 300 is equal to 0. So now we break this 300 into two parts, is minus 30 and minus 10. So here we can write V1 square minus 30 V1 minus 10 V1 plus 300 is equal to 0. So here V1 we take in bracket V1 minus 30. This again minus 10 I take in bracket V1 minus 30. This is equal to 0. So we get here, by solving it, we get V1 minus 30 into V1 minus 10 is equal to 0. So after solving this, we get here. So V1 is equal to 30 or V1 is equal to 10. So we have found out two values for V1. Now for this V2, from this equation 1, V2 is equal to 60 minus 2. Now if we take V1 as 30. So 2 into 30. So V2 is equal to 60 minus 60, that is 0. Or V2 is equal to 60 minus 2 into 10. So V2 is equal to 60 minus 20, that is 40 meters per second, and this is 0 meters per second. And V1 is 30 meters per second and V1 is 30 meters. So we have got two values for V1, 30 and 10, and two values for V2, 0 and 40 meters per second. So these two fragments, the two values which we have obtained is velocities may be 30 meters per second or 10 meters per second. And the velocity of the second fragment is 0 meters per second or 40 meters per second. Now, here we can see that this is 30 meters per, if it is 30 meters per second, the velocity of the first fragment is 30 meters per second, then the velocity of the second fragment, which is of 1 kg, is 0 meters per second. And if the velocity of the first fragment of 2 kg mass is 10 meters per second, then the velocity of the second fragment of 1 kg mass is 40 meters per second. Now, logically, this mass of 1 kg is smaller than the mass of 2 kg. Hence, the velocity for the 1 kg mass should be greater, but here the velocity is becoming 0. So, this is not a possible case. So, hence this is also not a possible case. Hence, the velocity of the 2 kg mass is 10 meters, which we can understand, which is lesser velocity, and the velocity of the 1 kg mass is 40 meters per second, which we can understand is more velocity than the 2 kg mass. So, the correct answer to the problem will be the velocity of the 2 kg mass is 10 meters per second and 1 kg mass is 40 meters per second. So, we complete the problem. Thank you.